We're going to look at solubility equilibria. We're going to define a solubility constant. We're going to call it Ksp. So you put a solid in water, for example, calcium fluoride, we put in water, will become calcium ion and fluoride ion. So notice that from the formula of the calcium fluoride, we have 2 in our formula, and so then we have to remember to put 2 in front of the fluoride ion. So this means that you really need to know your nomenclature because you need to be able to have a balanced equation to do this properly. At this point, no more solid can dissolve. The solution is said to be saturated. Now remember, the solids are not included in the equilibrium expression. So if we set up a Ksp, it would be equal to the concentration of the calcium ion times the concentration of the fluoride ion. And then remember that because we have 2 of the fluorides, we put that as a coefficient. And then this happens to be the value of the Ksp for calcium fluoride. The solubility is an equilibrium constant and only has one value for a given solid at a given temperature. The solubility is an equilibrium position and has an infinite number of possible values at a given temperature. Okay, so let's do a problem. We're going to set up a table so that we can keep track of the numbers. So what we want to do is put in the formula, in this case for bismuth sulfide. It's in equilibrium, and then we use our formula to put the numbers in. We're going to have 2 of the bismuth ion and 3 of the sulfide. So in this case, we're asked to calculate a Ksp value. We don't have any initial values, so we're not going to use the I row of the table, but we will use the change. So because there's a 2 here, we're going to have a plus 2x. Because there's a 3 here, we're going to have a plus 3x. And then our equilibrium will be 2x and 3x. And notice that this is left blank. And it's because it's a solid. So now we're going to set up our Ksp expression. We have bismuth, and because there's 2 in the equation, we will have 2 as the exponent. Because there's 3 in the balanced equation, we will have 3 as the exponent. Then we're going to calculate the concentrations. So we have, look at the column for the bismuth. We have a 2x. So this value that was given in the problem is the x. We'll take this value and put it in for x, multiply it by 2, and get our equilibrium for the bismuth. Since this value is the x, we also use it for the sulfide. We said sulfide is going to be 3x. So we put our 3x here. This is our x, so we put it in here. And then we will solve for our equilibrium value for the sulfide. So now we have the equilibrium value for the bismuth. So this is our equilibrium value for the bismuth. This is our equilibrium value for the sulfide. So we will take the molarity of the bismuth, put it into our Ksp expression, and remember we have an exponent of 2. We will take our molarity of our sulfide and we will put it into our Ksp expression, and remember we have an exponent of 3. We do the math, and then this is the answer. Now notice that the exponent is to the minus 73. You're going to get numbers that are very small. So don't be afraid when you get this number to such a very small exponent. That's very common. Okay, let's look at another problem. The Ksp for copper 2 iodate is 1.4 times 10 to the minus 7 at 25 degrees C. We are asked to calculate the solubility at this temperature. So you're going to want to know your formula for copper 2 iodate. So you're going to write that in your table. Remember to put the solid and then your equilibrium expression. So from your formula, you would have a copper ion being made. This is specifically going to be copper plus 2. From your formula, you're going to have 2 of the iodates. Now what we can do in this case is we can go ahead and use an ICE table. So this column is always going to be blank. And then we can put in a 0 for the copper and a 0 for the iodate. Then using the balanced equation, we have a plus x and a plus 2x. And so our equilibrium is x and 2x. We set up our Ksp. The Ksp is going to be copper ion, iodate ion, and remember it's going to be squared. And then the equilibrium row told us that there is an x here. And remember, inside our brackets, there's a 2x. So what you're doing is you're taking this x and putting it inside here. You're taking this 2x and you're putting it inside here. When you do the math, you've got x times 2x squared. That ends up being 4x cubed. And then when we solve for the problem, we're going to take the 4x cubed that we got here, and we're going to set it equal to the Ksp that we were given in the problem. So that goes here. Then we solve for x. The x is our solubility, which is what the question was asking for. So you're going to want to take whatever salt is given, use the correct formula, use the equilibrium arrows, break up the salt into its ions. Remember to put your charges in here. Remember also to use the formula so that you can balance the equation. You can always go ahead and use an ice table. And then initially we would have had 0, 0. And then remember, use your coefficients to get the proper plus x's. And then remember that your x's go inside your brackets. So in this case, when we do that, we want to be sure and put them inside the parentheses here. And then this one also inside the parentheses here. And then you also want to remember and use your coefficients. So in this case, the copper ion was a 1. So you can leave it like that. And then in this case, the iodate was a 2. So put that there. And be careful doing your math. And then you should be able to solve for the x. And if you look on your calculators, a lot of calculators have buttons that you can use to take the cube root. So what you're doing, we're taking this and we're going to divide it by 4. So we're dividing it by 4. That gets rid of this. And then we can take the cube root of this, and we can take the cube root of this, and you should be able to find a button on your calculator that does cube roots. Okay, that's enough for this time.